My name is Travis Connor, and this is Lab 4, Oscillations. In this lab, I used Tracker to observe the motion of a spring mass system oscillating in 2 dimensions. I also created a computational model of the situation in ClosScript. The purpose of this lab was to investigate the motion of a spring mass system oscillating back and forth. The fundamental principles used in this lab were Newton's second law and the energy principle. The main result in this lab was that the total change of energy in the system is zero, meaning that the energy principle was maintained. There are many different equations used in this lab which can be seen now. Newton's second law had 2 components, the force due to the spring and the force due to gravity, and their equations can be seen. The energy principle states that energy cannot be created or destroyed, and with the energy principle, the total change in energy was zero, meaning that the change in kinetic, potential, and spring energy equaled zero when added together. Additionally, there were other equations used such as the change of velocity equation and the change of position equation, which are derived from Newton's second law. In this lab, the system was the mass, spring, and earth, while the surroundings were nothing. The initial conditions for this lab were that the mass of the object was 0.402 kilograms. The object started at negative 0.118 meters in the x direction and negative 0.633 in the y direction. The object started at rest. The spring constant was 6.83, and the relaxed length of the spring was 0.123 meters. In the experiment, I used Tracker to track the movement of the mass oscillating back and forth in the video. I tracked the position of the object in each frame. This allowed me to identify the movement along the x and y axes and plot each point. I then placed this data into an Excel spreadsheet so it could be used later in the computational model. Now, moving on to the computational model, I edited the code on the right so that the spring length could be identified, which could then be used to obtain the spring energy from the spring. I did this by using the spring equation. I then edited the next lines with the formulas for each type of energy to get the total system energy. These are the equations displayed earlier. On the left side, the motion prediction can be seen. I edited the lines so that the change in energy could be obtained, thus allowing for the mass to move in the simulation. These lines of code use Newton's second law and also the energy principle. I used the FNet formula and also the velocity and position update formulas. I was able to use these formulas because the change in time, or delta t, was very small. Here the results of the simulation can be seen. We can see that the model motion in the x and y directions is perfectly oscillating. However, the experimental motion in the x direction is slightly off from the model, and the experimental motion in the y direction differs greatly from the model data when in the upward direction. The results of the model also show that all the different types of energies were conserved. Some possible sources of error are that when using Tracker, my placement of points could be off, meaning that the observational data would be off. Another source of error could be that the real-life situation is not a closed system, so influences such as air resistance could affect the outcome. The answer to the question, is the energy principle satisfied, is yes, based on the data received from the computational model. This follows the energy principle. When comparing the oscillation periods in the x and y direction, the x direction had a longer period, resulting in a smaller spring constant than the y direction.